Welcome back, everybody. This is the last video in the testing module for Software Engineering 1, and today what we're going to talk about is testing specifically around default prediction and some metrics that you can use to kind of empirically understand what to test. So far, the main kind of idea that we talked about is that testing is absolutely critical. If you talk to any software engineer at any software engineering company, they will absolutely tell you that. But it's kind of understood and not talked about very often that it's intractable to actually test every piece of an application, especially when the application is fairly large. So what we've been going over this week is really kind of procedures that you can use to prioritize testing. And you can do that based on either code by looking at glass box approaches that effectively go line by line in problematic pieces of code and test them, or branch by branch or whatever. And we also talked about approaching testing from a specifications perspective, which is called black box testing, where you basically put yourself in the shoes of a user and you go through as many of the use cases and as many of the processes as you can and verify that your experience is acceptable. And so we also talked about how important it is for acceptance criteria to be given to you by the business team in those cases, and all of that stuff is kind of in the second video. So what we're going to do now is we're going to talk about some specific kind of quantifiable metrics that you can compute to help you with the idea of prioritizing testing. And we're also going to talk about kind of practically why it is important to not do intractable things. And then we're going to end with a brief discussion of all of the different kinds of testing that you might hear as sort of buzzwords in the industry. So first of all, a lot of this stuff is based on a field of software engineering research called defect prediction. This is going to be something that we're going to talk about in the research in software engineering module in a couple of weeks. Basically, the idea is if you can take a look at a piece of code, you can take a look at its history, and you can take a look at the people who have contributed to that code. You can gain an idea of how likely it is to be defective based on some of that data. So we're going to talk about how code that has more code to it, so longer pieces of code, or code that is more complicated, are likely to be more defective. And so it's very easy to kind of prioritize those pieces of code over simpler pieces of code. So what you want to do is you want to use defect prediction either when you are just starting off a project, or if you're trying to kind of bring a project back from the brink. So a lot of times what will happen is you will get added to a project that's in flight. And if you're getting added to a project that is in flight, either the project is ramping up or the project is trying to onboard new people because somebody's left the team, or they're trying to onboard new people because they feel like they're falling behind. And in the case that they're falling behind, very often the amount of technical debt that the project is under is substantial. And code metrics can help you kind of minimize the amount of time that you're spending on specific pieces of code if they're known to be fairly stable. So defect prediction is helpful for the very beginning of a project, but it's also helpful if you've sort of been coding for a while and you're on iteration 3 and you kind of identify that you're not going to necessarily make it with all of the features. You can prioritize the features that are the closest to done, or you can prioritize the features that are the least close to done, whichever you think will be better for the client. So code metrics themselves are quantifiable metrics, or they're quantifiable aspects of code that you can use to determine the relative quality of a piece of code. And so what we're going to talk about first is a complexity metric. So if you have two artifacts, you have two classes, for example, and one of those classes in its main method has 517 nested ifs, and those are all inside of 3 nested loops, that is going to be a vastly different situation than maybe a different artifact that only has a single conditional statement. And so colloquially, just from your experience doing programming assignments or doing kind of programming as a hobby, you might think that the 517 nested ifs inside of 3 loops is going to be much more complex. It's going to have much more potential code paths, and it's going to pose a larger risk to being defective than a very simple piece of code. Complexity metrics allow you to understand this at the project level. So it can actually tell you the top 15 most complicated methods or the most complicated classes in the project. And what that does, that allows you to kind of hone in on those specific pieces of code. There's no way that you're going to just off the top of your head recite the top 10 most complicated pieces of code in a software system that has maybe 500 or 1,000 or 10,000 classes in it. So if you had your choice and you had maybe an hour or 2 hours to do some testing, obviously testing on artifact A is going to yield more fruit. If you find an issue in artifact B, you're probably going to do it very quickly. If you move from artifact B to artifact C or D or E that has the same level of complexity, you're likely to go through those very quickly, but you're not as likely to find actual problems. Artifact A is much more likely to have problems because it is so much more complicated. The downside of this, and really the upside of using metrics, is that these complexity in general is not as easy to determine as this. So you might have 3 classes that both have nested loops, but the number of branches inside of those nested loops may not be easy to calculate unless you have like an automatic routine for calculating the specific complexity metric. And what you want to do is you want to get away from kind of anecdotal concepts of your code and more towards something empirical. You want your IDE or you want your build system to actually identify for you the most highly complicated pieces of code that you can get the most fruit out of testing. So the easiest complexity metric that in existence is lines of code. So it's very, very simple, and literally what you're doing is you're testing based on the largest pieces of code. And so there are many, many different definitions of lines of code. Typically you exclude things like opening and closing braces if they're on an individual line. What you want to do is you want to hone in on very large pieces of code, and you want to do so because just from a statistical perspective, it's much more likely that a larger piece of code has more bugs in it, and there's more opportunity for bugs. You can also hone in on these pieces of code for refactoring. So if you identify that this one piece of code is very likely to contain bugs solely because it's huge, you can split that piece of code up into smaller pieces. That helps with encapsulation, it helps with coherence between your system components, and it will also push that piece of code down further on the prioritization stack for testing. So it kind of helps you understand what is actually a high-risk failure in your system versus what is just a huge piece of code. So you can either use it as a prioritization for testing, but also for refactoring efforts if you have the time. So there is an alternative that's slightly more complicated than lines of code called cyclomatic or McCabe complexity. Basically what this is a count of the number of branches that are generated when the code is compiled. So you can basically think of taking your high-level language, converting that into assembly language, and then counting the jumps and counting the branches. And this turns out to be an extremely good predictor of faults, even though it's fairly simple, right? It's very easy to compute. You can go out to GitHub, you can go out to Bitbucket. There are many plugins to things like Ant that will flag a code for you based on this, and it's not like rocket science to count branches. The interesting thing is that there is empirical evidence that if you test the cyclomatic complexity of a piece of code and the complexity is higher than a 10, that it is statistically significantly more likely to have a defect than a piece of code with a complexity score less than 10. So there are very well researched and established guidelines for what you should invest time in testing. And in the case of McCabe complexity, 10 tends to be the sort of higher end of what you should expect to be non-defective in production code. So if you think about the difference between the cyclomatic complexity score and the lines of code, it's very related. The two are highly correlated with one another because as your size of the code extends or as you get bigger, you're more likely to have more complicated branch instructions inside of that piece of code. So there are tons of studies that have challenged the usefulness of McCabe, and it's solely because of this correlation. It's unclear if the branches are the cause of the bugs in a lot of cases, or if the length of the code has resulted in a bunch of branches that wouldn't otherwise be there. So there historically have been a couple of fights around, is it actually worthwhile to implement McCabe complexity now that there are so many plugins and now that there are so many well understood kind of algorithms for computing it. There isn't really a downside. You can actually compute both of them and use both of them in a kind of data driven decision on what you want to test inside of your system. So beyond code metrics, just to back up a second, there are tons and tons and tons of code metrics. There is a huge body of research in defect prediction. There are AI models, there are Markov chain models, there's all sorts of research being done on how you can predict the faultiness of a piece of code, and by extension, all of that research can be applied to prioritizing testing. If you have the ability to build a model and the model can tell you if your piece of code that's the input is faulty, you can always push that higher in the prioritization stack for testing. So we're going to talk about some of those in the research module. It's in a couple of weeks, but if you're interested, I could give you a ton of resources around specific metrics that you can use for your code. Beyond code metrics, what we also want to talk about is something that we started with in the first video, and that is non-execution based testing. So non-execution based testing is literally just you sit down with your code, you read through it, and you try to logic out any issues that are with the code. This happens in two main flavors. One of them is kind of before you check in, you review the code to make sure that you're not doing anything untoward. So you're trying to adhere to the coding standards potentially for the organization. And the second is code reviews. So if you are a junior developer, particularly in a large group, usually everybody needs a code review. But code reviews are basically you and your team, or maybe a subsection of your team, all kind of gather around your monitor. You sort of sort out what you've done in the code, and then you get multiple people's sort of input on how you've managed to fix a bug or implement a feature or whatever. Tons of tools like GitHub and pull requests allow you to do this remotely, so you don't necessarily have to be around a literal computer. You can submit a pull request, and then however many people you need can code review that pull request, suggest edits, and then after those edits are made, they can sort of adopt it into the system. So the interesting thing about non-execution based testing is that you don't actually even have to have a runnable system. So if the system is half-baked or 10% baked, or if the system is so far off the deep end with technical debt you can't actually even execute it, you can still perform non-execution based testing. This is a great example of something that the textbook goes to a lot of effort to kind of classify or build taxonomy around. But everybody kind of performs non-execution based testing without actually even recognizing or calling it testing. So it's important to remember, though, that all the time that you spend looking at your code prior to checking it in, or looking at your code prior to compiling and running it again, is actually testing. You are actually getting ROI because you're actually building better quality software as you kind of iteratively read it. So if you think about it kind of generally, code reviews themselves are effectively crowdsourcing debugging. You have not only your experience, but you also have the experience of the 10 or the 15 or the 20 people on your team. And very often this leads to much more rapid fault detection. So somebody's experienced a bug that you haven't experienced before, they can identify it in your code, they can tell you how to fix it. It also serves, code reviews also serve as really good cross-training. So if you have, for example, an architect that's in your group that is reviewing your code, they're much more likely to give you kind of the big picture idea of how your code could fail, and it's a really good way of kind of becoming an intermediate or a senior developer. Having constant kind of feedback on your commits will always kind of make you better. So at the root of it, software engineering is a business, and so the biggest thing is you don't necessarily want to spend somebody's annual salary trying to test things if you don't get anything out of that testing. So we've talked in the first and in the second video about how if you are an engineer and you go to test your own code, you're very likely to test the things that you know work because it makes you feel good. That isn't necessarily a benefit. You're not actually getting anything out of that testing. Every time you perform testing, you don't find anything. That's a confirmation that everything's going well, but you didn't actually mitigate any risk. So what you want is you want to make sure that you're prioritizing code and specifications and everything like that it could be likely to fail, because every failure that you find is a failure that the client will not find, and ultimately leads you to better results. So if you overspend on testing efforts, then you can have less time to actually go to market with a good product, or you can have an overage that is specifically caused by that testing effort, and then you have to explain to the client why you were testing a method that only has one line of code when you could have been doing something else. So the sad state of affairs is that often projects run over. We talked about this very early in the semester. Maybe 60 or 70% of the time projects have overages, and it's important to realize that testing, it traditionally happens at the end, and as you compress the timeline for your project, testing is usually the thing that goes the first. And so you don't want to get to the situation where you leave all of your testing for the end, and then you don't get to test, and then you go to market with an untested code base. But you also don't want to spend so much time on testing that you don't have time to actually implement all the features. And so the group project will absolutely teach you about those two extremes. And what you want is something in the middle. You want enough testing to solidify the code, to ensure that bugs that are reported are not very bad bugs. They certainly can be inconveniences, but you're not going to lose data. It's not going to be a security issue or something like that. And you don't want to spend so much time testing that you're wasting resources that could have otherwise gone toward additional functionality or delivering early, which I think is sort of an unheard of thing. Everything in software engineering ultimately comes back to cost benefit. And if you're spending too much time testing, it may seem like there's no such thing, but it actually can be very detrimental to a project. It can lead to overages, and it can also shorten the amount of resources that you have to actually finish the project. So we talked about this a little bit too. So what you want is to identify high fault code outside of your testing process. So you want to be able to have links that establish the most complex piece of code with something like a code metric. You also want to understand how many defects that piece of code has had over time, and if that trend has changed. So if it used to have 500 bugs and now it's had 2 bugs the last 3 iterations, that's excellent. If it's on the upswing and now it's constantly having more bugs, that can obviously tell you that there's something that needs to be corrected in the process. And you also want to identify code that frequently changes. And so going all the way back to sort of agile methodology, if your goalpost is constantly moving, your code is probably constantly moving to move toward that goalpost. Your tests are probably constantly moving. And so as the volatility goes up and down the sort of life cycle, you need to be aware that these constant changes can break tests, they can break pieces of code, and before you go to market or before you release the code, you need to make sure that all of this volatility slows down. And ultimately, it is the management of the software company's job to understand when enough is enough. So what I mean by this is there will always be a piece of code in a system that is absolutely the most brittle piece of the system, bar none. So you can imagine a piece of code that has 500 bugs, and it will always have 500 bugs from version 1 through version 35 of the application. And at some point in time, someone in management or an architect or a senior developer has to be like, hey, we've spent months and months and months trying to fix this piece of code. Maybe it's time to bite the bullet and recognize that there's some sort of underlying architectural debt or some sort of underlying technical debt that needs to be addressed through either refactoring, like a major refactoring of the code, or a major redesign of the aspect of the system that the code is built to implement. So what can often happen is if the project is being pushed by the client will always want a quick fix. If you put a bunch of quick fixes together, you typically end up with a lot of technical debt. At the end of that, technical debt can get to the point that it's easier to actually just re-engineer or recreate the piece of software than it is to continue to maintain the piece of software. Ultimately, the job to navigate that is with the management of the software team. So to put a cap on testing, I want to go over the kind of different types of testing that you will very frequently hear about in industry. So to recap, integration testing is basically testing the integration points between the subsystems of the system that you're creating. So that's all the kind of modules that add up to your system, and making sure that they all communicate with one another correctly. But it's also all the integration points between your piece of code and all the third-party libraries that you're using. So if you're using the Twitter API to scrape data, or if you're using Google Maps to understand location awareness, you need to make sure that there's a testing plan for every point where your code interacts with one of those third-party libraries. In doing that, you want to make sure that you check all of the API calls, because API calls could change, particularly APIs that are hosted. There's a well-known issue with Dialogflow where Dialogflow 2.0 is not compatible with Dialogflow version 1.0. If you didn't check those API calls and Dialogflow version 1.0 was sunset, your application would just suddenly cease to work. So that's not a good situation to be in at all. But you also want to check things like database interactions, file system interactions, that kind of stuff, because as you are building your piece of software, the client is also living their life. So they could be upgrading to the latest and greatest database engine, they could be changing file structures, they could be doing all sorts of stuff, and you want to make sure that your integration testing is identifying issues that will come up once you give the piece of software to the client, either for UAT, for acceptance testing, or for them to actually use in production. So it's important to remember that if you skip integration testing and you have flawless testing, unit testing, what can happen is you will have the world's greatest units, but they will not talk to one another. And so you'll have pristine code that is not functional. And so obviously you're not going to get paid until you can make sure that all the integrations actually work. So smoke testing. Smoke testing is an idea that comes about when a project gets down to the wire and people want to say that they're testing, but they're not actually testing very much. So the idea of smoke testing literally comes from manufacturing, where you would maybe have cars coming off of an assembly line. You would go to the car that's created, like the 5th or the 6th or the 7th car on the day. You would turn it over, and as soon as the car started and didn't immediately catch fire, everything is considered completely fine. This is often the very first thing that will happen once you have kind of given up the ghost. If you recognize that you have too much code to test, your a timeline is too short to actually perform any of that testing, and you don't have clear guidelines for testing, like you have no automated testing, and you're kind of in a world of hurt at this point, smoke testing is basically what people always resort to. The idea here, though, is if you have a patch that's very critical and you need to get it out to market, if you have only changed 1/2 of a line, like you changed a plus to a minus, theoretically, if your architecture is sound and if everything is put together correctly, smoke testing that one component before releasing the piece of code should be sufficient, should be all you need. But typically people overuse smoke testing. They'll change maybe 5 or 6 different things. They'll have not perfect architecture, and then they'll perform smoke testing, miss stuff, and then even more bugs go out into market. So once a firm starts doing excessive smoke testing, you typically see a spike in technical debt, a spike in architectural debt as they try to respond to that technical debt, and then continued instability in market. And there are tons of apps that you can find that have the same problem. So package testing happens after testing of the actual application. So package testing basically is answering several very niche questions. So if you have a desktop application, does the installer for the desktop application work? Does your application actually start with no data in it? So if it's the very first time that you have launched the application, do you have to go and change some config file somewhere, or can you just double click and everything kind of works? Can you access the installer as a person who isn't authorized to access the installer? So making sure that you aren't giving pay to use code away for free, that kind of stuff. Can the user actually make a payment to receive the installation package? And things like, are you being clear with potential users about the platforms that you support? So if you only have an application for Android, if you don't make it very obvious that iOS users can't use it, you're obviously going to have some problems if a person pays to use the application and they can't. That usually gets circumvented because of the application stores, but you could potentially have enterprise level software where you're circumventing some of that sort of like framework app store stuff. So package testing, the idea is you've done all of the hard stuff and now basically you're trying to get the code from point A to point B, and is it true that the user can actually install and use the application with all the sort of interstitial supporting stuff around it. So acceptance testing happens on the client side, the business team side, and so basically what will happen is the quality assurance team on the software side is using test data most of the time. They're using their own infrastructure that's internal to the software team. And at acceptance testing, what will happen is all of that stuff will be given to the client and the business team. The business team will use the actual infrastructure, usually a test infrastructure system, and they will use their own data. And what will happen is the client will then report any issues that they find in acceptance testing back to the software team. And what you want to do is you want to make sure that wherever possible, the only issues that they uncover are really because of this difference in data or the difference in infrastructure. If the client continuously finds kind of easy to identify bugs, what will ultimately happen is the business team will lose interest in working with the software team, or they'll lose confidence in the entire project because they recognize that there is a wholesale kind of lack of testing that's happening on the software side. So this is the first point where a client or where an end user will recognize that potentially excessive smoke testing is happening and you're not actually doing your end of the bargain as the software team. Acceptance testing typically happens in kind of enterprise level projects. So as you know, if you've downloaded like an iPhone app, you don't typically get to do acceptance testing. It's kind of informal. Basically what will happen is you will get the update pushed. If you don't like it, you'll go onto the App Store and give a bunch of thumbs down reviews and then hope that the software team will fix it. In larger engagements, like you're going to build a banking app or something like that, what will typically happen is a formal process happens where there's handover, and then at the end of acceptance testing, the business team either accepts or rejects, and at the point of acceptance, then usually the contract is done, the client will pay the remainder of whatever they owe to the software team, and then the end users of the client, so the actual tellers at the bank, or the actual people who have their money in the bank will begin using the system. And that is when the system is actually at market. So at that point, they can raise issues, they can raise feature requests, but mostly those things are handled as a maintenance engagement, which we'll start talking about next week. So at this point in the semester, we have talked about analyzing, planning, implementing, and testing the system. So we've gone all the way from gathering requirements for potentially a situation or a system you have no idea about, like PNC insurance, and going through implementation and testing that piece of software. So after acceptance testing, or once your internal acceptance testing is done, what you're ultimately going to do is push this thing to market. People are going to start buying it or installing it and licensing it. So typically people think of that as kind of the end of the story. However, what we're going to do next week is talk about what happens when the client finds issues in a piece of software that they've already paid for. So there are bug requests, there are feature requests, there are all sorts of things that happen after an application is in market, and those things can continue to happen for decades potentially. And so there is an internal structure within software organizations to handle all of that stuff. It's called support and maintenance, and we will cover that in a lot of detail next week. So thank you very much for tuning in, and I will see you then.